In the last class, we have read that how we can design the combination circuits. What is the conventional design procedure, and we have seen a comparator design. Now, today we will see how the common circuits such as some very popular circuits and very important circuits that adder, the different type of adders can be designed, because these adders are nothing but the combinational one. So, as its name implies, the addition consists of the adder does the addition operator, and this consists of 4 possible elementary operations, and these operations are say there are 2 bits. Say this is, so addition we are as if there are 2 operands A and B, we are taking the addition. Say I am giving the addition notation as plus. Now, this is my A value and B value. So, if it is 0 plus 0, then my sum means the output is 0. If it is 0 plus 1, the sum is 1. If it is 1 plus 0, it is 1, that means these are binary addition, and 1 plus 1 means 1 0, sum is 1 0. Now, if we just express this sum by 2 bits, because that 1 plus 1 is 1 0. The remaining 3 we can represent by single bit. So, now if we represent this by 2 bits, so this is my 2 bits sum 0 0, 0 1, 0 1, 1 0. So, what will happen? Say now, say there are 2 bits, this is one LSBs, I can tell this 4 and this is 1. So, if I add A and B, then this is my, if my sum is realized by only 1 bit, then this LSB, the lowest this bit, that means that 0 1 1 0, these I can define as my sum bit, normally denoted as S. And so, this 0 0 0 1, these we are called that carry bits, normally noted by C. So, given this problem of addition, now how we can write my adder? Say if it is, I am considering one half adder, and the half adder we define as if there are 2 operands for addition and there is no previous carry, that means only 2 values are added and the operator already operation we have defined. So, here as if we are now identifying that there are 2 operands A, B, they are the inputs, there are 2 outputs, one is my sum and one is my carry, and this is my half adder I am telling, because I am not considering the previous carry bits. So, now we can write in this way. So, again the way in the last class we have defined. So, if the half adder is a one function, this f, I can partition this thing by 2, because there are 2 output So, I can define this as F1 F2 and this F1 gives you S sum, F2 gives C, and as if both are fed by AB. So, now if we draw the maps, if I draw the maps, then what will happen? Say for the carry, so there are two inputs. So, there are two inputs, say B. So, this is for my carry. Then this is 0 1 0 1. So, for 0 0 carry is 0, 0 1 carry is 0, 1 0 carry is 0, 1 1 carry is 1. So, only that C equal to AB it realizes. Similarly, if we draw the map for my S, what will happen? Again I am taking AB, this is for my S, 0 1 0 1. See, for 0 0 sum is 0, 0 1 sum is 1, 1 0 sum is 1, 1 1 sum is 0. So, for this what will be there? That A B dash. So, my S equal to A B dash plus for this the min term is, for this one the min term is A dash B. So, that we have written that S equal to A dash B plus A B dash and C equal to A B. So, this is my half adder circuit, and remember that was our the last quiz question, that design a combination circuit that performs the addition of 2 bits called the half adder. A previous carry bit is not considered, mainly there are 2 inputs. So, if we realize, the realization is very simple, because A B dash plus A dash B, and now again I am assuming that my complemented as well as uncomplemented variables or literals are available, then this is a 2 input AND gate and 1 2 input OR gate. So, my S is that to A B dash and A dash B, and they are OR, and so this is my S, and carry is simple, C equal to A B. So, in this, just to generate the sum, there are two input AND gate, two number of 2 input AND gate, and 1 2 input OR gate. And in the carry part only 1 2 input AND gate. That is my circuit. Now, we see that this is a very simple circuit, that where we have done that A B dash plus A dash B. Now, this A B dash plus A dash B, that we can write in different way. See that I have written S equal to A plus my S was A B dash plus A dash B. Now, see, I have written A plus B into A dash plus B dash. Say if I apply the distributive law, then this is A dash plus A B dash plus A dash B plus B B dash. Now, A dash and B B dash, that will be 0. So, this becomes A B dash plus A dash B. So, that means my A B dash plus A dash B, that I can write as A plus B into A dash plus B dash. Means again this is one AND gate, 2 OR gate, which is the reverse of the previous one. In the previous circuit it was 2 input AND gate, 1 2 input OR gate. Now I am realizing this by 2 input OR gate and 1 2 input AND gate. See that A plus B and this is A dash plus B dash, 2 input OR gate and then 1 2 input AND gate, and carry remains the same. So, the total number of gates are same. So, this is a different type of realization of the half adder. Now, we see another. See that my carry is A B, my carry is C is A B, and my sum was A B dash plus A dash B, and that I can write, because see A B dash plus A dash B is nothing but 2 input XOR, 2 input XOR A B. So, that I can write that A B dash plus A dash B dash dash, means we know that A equal to a complement of complement, means that this is the twice I have taken that complement value. So, what will happen? That means my S sum again, if we write, this is A B dash plus A dash B, and this is I can write A B dash plus A dash B complement of complement. If I compute this, this is nothing but X naught, and we know that 2 input X naught is A B plus A dash B dash, that complement of that. Now, see this A B means this is my C, the carry, and this is one A dash B dash and complement of that. Now, this see the same, that thing has been realized. So, this is the carry, as it is that A B carry is there. Now, the carry I am taking as the one of the input, and the other input is coming from a 2 input AND gate A dash B dash. So, again it is fed to the OR gate. So, see this is C plus A dash B dash, and now it is complemented. So, one inverter is put. Now, this is, now see here only 4 gates are needed. So, this type of realization, if we do this type of realization, then my half adder circuit takes only 4 gates, that 2 input AND gates, 1 2 input OR and 1 not. So, total inputs are only 4. Initially it was 17 inputs. Always we are assuming, in all the circuits we are assuming that the variables are available both in complemented and uncomplemented form. So, again see, so this type of realization, that number of gates are very much reduced and these are only 4 basic gates. Whereas, in the previous design, see that the gates are, again they are 4 gates, but the different type of gates. Here we have used that inverter, one inverter we have used, and AND gates, and one OR gate or one AND gate, that we have reduced. Now, this is again another realization. The sum is same, that a plus b into a dash plus b dash, already we have discussed this sum part. Now, carry is a dash plus b dash. How? This is simple, that carry was a b. So, if we apply the De Morgan's law, then C dash is, this is a dot b. So, this is C dash is a dot b dash, and it will be a dash plus b dash. So, that thing we have done, that is C equal to a dash plus b dash. See here what happened, that only 2 OR gate, 1 AND gate, 1 inverter. That means the different, mainly AND, OR and NOT, these basic gates we are utilizing, and the number, only the numbers of OR or numbers of AND are varying. Now, this is another realization possible. See what was my expression for that sum, that is nothing but a b dash plus a dash b, which is and 2 input XOR, that a b and this is my sum. So, that is realized by simple XOR gate, and a b, the same input I am taking, then C equal to a b. Now, what is the advantage of that thing or disadvantage? See, first thing is, here there is no need that complemented variable should also exist, only we have taken the uncomplemented variables or the letters, and there carry is simple a b and one XOR functions. So, there are 2 gates, but just notice that here that this XOR is not a basic gate, that this is a actually that AND OR sum AND OR realization is needed for this XOR. But now, for these MSI circuits, that actually that we can realize the circuits by XOR, XNOR or multiplexer or different type of many other, that ROMs, that is also nowadays available. So, if my MSI circuits, MSI means that medium scale integrated circuits, that where instead of the basic gates that AND or NOT, that XOR gates, XOR and XOR NOR are also available, then we can easily utilize, or you can easily use this type of circuit for half adder, and see there are only 2 gates are needed for that. So, this is the minimum thing, that there are only 2 gates are necessary. Now, we see a design of a full adder. Now, a full adder is a combination circuit that does the arithmetic sum of 3 inputs, 2 operands A and B and 1 previous carry. Now, what do we mean by this? See, earlier in the half adder we have only taken, say as if we have taken two operands A B, say 0 A is 0, say B is 1 and it is adding 1, sum is 1 and carry is 0. Now, this is simple 2 input, or we can take single adder. Okay. Now, what we am say my AB I am adding, say I am adding, again I am adding A, but this A has 4 bits. This is my A, say as if this is A0, A1, A2, A3. Similarly, these are B, so I am giving B0, B1, B2, B3 and as if I am adding say as if I am adding this. So, obviously, it will generate a 4-bit sum. That means S0, S1, S2, S3. So, this type of circuit. Now, we are defining, in this case actually the half adder will not be sufficient, because if we take one example now, see my A is 4 bit, A0, A1, A2, A3. Actually, we should write in different order. LSB first, A0, A1, A2, A3. Similarly, the B is B0, B1, B2, B3. Say I am taking now some values. Say A is say 0, 1, 0, 1. Say my B is 1, 1, 1, 0. Now, I am adding. Now, see, I can treat or I can take this A as if 4 single input adder, because these are 4 or one input adder or 2 input adders. That means, here only one single input of A0 and B0 I am adding. So, this is 0 plus 1, 1. Now, already we have defined that if it is 0 plus 1, 0 plus 0 is 0, 0 plus 1 is 0, 1 plus 0 is 0, 1 plus 1 is 1, carry 1. Here all the carries are 0. So, see now here there is no carry. So, it is not important. Now, 0 plus 1 again is 1, 0 plus 1 carry 0. Now, 1 plus 1, this is say the sum is 1 and there is one carry also. So, this carry, now this carry I have to, this carry will go here. So, when I will be adding, now actually there are 3 inputs. So, this is my B value, A value and this is my carry value. So, there are actually instead of 2 inputs, there are 3 inputs. So, this is again 1 plus 0, 1 and 1 plus 1, this is 0, again carry 1. So, this carry 1 will come here. Now, here the carries were 0, but actually that I have to consider. Now, all the carries will go here. So, instead of 2 inputs, now for the full adder I have to consider 3 inputs. So, that is why the full adder is defined as if 2 operands and the previous carry. So, C we are defined as if this is the previous carry, means the carry generated from the previous bits. So, these we can tell that the 2 operands, that 2 operands A and B, and the carry is actually the carry generated from the previous bit operation, bit addition. Notice here that in the half adder we have not considered that thing. So, half adder means mainly the single bit addition, and here actually the multiple bit addition. So, now we see that how we can design the adder. So, once it is the system is identified, again we can tell that my system is, now this is a black box, there are 2 operands A, B, and this is my previous carry, this is my sum, and this is my carry, means the next carry or the carry to the next bit. Okay. So, this is my So, now we identify the output input relationship. See that these two are the operands A, B, and this is the carry. So, 0 0, if the carry is 0, then again 3 0 actually we are adding, and sum is 0, carry is 0. 0 0 1 means sum is 0, carry is 1, carry is 0, sum is 1. 0 1 0, sum is 1, carry is 0. Similarly, 0 1 1 means now 1 plus 1. So, sum is 0, carry 1. So, in this way, for all possible combinations of 3 inputs, means the 8 combinations will be there, that we have found out the what will be the carry and the sum. Now, again here the actually the F, the system F, that has been partitioned into F1, sum, and F2, carry. A, B, C are the inputs. So, F1 means that A, B, C are the 3 inputs and the carry is the output, and A, B, C are the 3 inputs and sum is the output, that is my F2. So, again now we draw the Carnot map. So, first we draw the expression for sum is. Now, again that if we see the sum, that where it will be 1, it will be 1 for the decimal value, that 1, then 2, 4 and 7. So, for 1, 2, 4, 7, see for 1, okay, if I take in this way, so I give this is my A and this is B, then actually this should be A, B, C. There are 3 inputs. There are 3 inputs. So, this should be A, B, this should be C. So, this will be the 1, this is the 2, 0, 1, 0, then this is 4, this is 8. So, for this 4 the output will be 1, that means one sum bit will be 1 and the remaining the sum bit will be zeros. So, if we now take the min terms for this 1 value, that means for where 1 is there, that min term will exist in the expression, then it will be 0, 1, 0 means that A dash, first we take A dash, B dash, C means this one. For 1, this is for my 1 min term, A dash, B dash, C, then A dash, B, C dash, this is for the min term 2, then A, B dash, C dash, A, B dash, C dash, this is for min term 4 and A, B, C for min term 8. So, these are the, this is the expression for the sum. And here they see there are no couple possible. So, there is no reduction from this. So, this is the expression for sum. Now, what will be the carry? Again, if we see that from the truth table, that for carry, for which value that carry will be, say this is for 3, carry will be 1, then 5, 6, 7. So, see 3, 5, 6, 7, again if I put A, B, C, so this is 3, then 1, 1, 0 means 6, 7, 5. So, this for 3, 5, 6, 7, the output will be 1 and remaining cases it will be 0. Then what will be the min terms? The min terms will be, say for here actually there is one couple possible. So, this will be A B, again this will be A C and this will be B C. So, C is, that means for this column it is A B, for this couple it is A C, for this couple it is B C. So, A B plus B C plus C A. So, these are the carry bit. Now, for the carry bit, now we have to see that what will be the design. First the sum. Now, sum was, see the sum was how many, 1, 2, 3, 4, 4 3 input AND gate and 1 4 input OR gate. Now, see so these are the 4 AND gate, 3 input AND gate, and its inputs are, that inputs are actually A, B dash, A dash, B dash, C, A dash, B, C dash, A, B dash, C dash and A, B, C. That means, both complemented and uncomplemented variables are available and one 4 input OR gate. So, this gives the sum. Now, the carry will be simple, that AB plus BC plus CA. So, the carry is that 3 2 input AND gate and 1 3 input OR gate, that will give the carry. Now, there can be other realization. See, here there was no reduction possible from the Karnaughan. Now, we see that what is actually that sum circuit. See, my sum was A dash B dash C, A dash B C dash, A B dash C dash plus A B C. So, if we take that sum expression, see, if we write the sum expression A dash B dash C, A B dash C dash, A dash B C dash plus A B C. Now, say from the first and third term, say I am taking A dash common, then similarly this is B dash C plus B C dash, and from the second and fourth, if I take A common, then this is B C plus B dash C dash. Now, already we have seen from the previous one example from the last class that this is actually B XOR C, and this example is actually X NOR, that means B XOR C complement of that thing. Now, see, if B XOR C I replace as X, B XOR C we replace by X, then this is nothing but A dash X plus A X dash, which is again A XOR X, and that will be A XOR B XOR C. So, that means my sum can be a 3 input, simply a 3 input XOR circuit, or that 3 input XOR we can realize by 2 input XOR. So, what will be the circuit? That means my sum circuit for my sum will be, say simple, I can take a 3 input XOR A B and the carry C, this is my sum, or it can be two input, that A B and C, then S. So, this can be a sum circuit. Now, see that C XOR A XOR B, already we have written that thing. And that we can also, that we can write already, this we know that we got this thing, and then that C we can write as that carry C, that is A B plus B C plus C A. See here how we can write, actually this is my A B and this is my B C plus C A. So, that also we can write in this way that C A B dash plus B dash A, and that is also A B dash C plus A dash B C plus A B. In this way also we can write my carry. So, now if we design this thing, that see that from here, actually from here I can take this thing. See, my half adder was simple XOR, or that was, see again we go back to our half adder. See our half adder, it was simple A XOR B and the carry was A B. That was the half adder circuit. That was the half adder circuit, because it was the truth table. So, if we from here we identify that thing, see this is from here A dash B C dash and A dash B C dash. See, this is, see from these two, this is nothing but XOR circuits. That means, this is C XOR A XOR B. Now, A XOR B, I can write that this is a half adder circuit. This is a half adder circuit. So, now we can realize that full adder with two half adders. So, see that thing, that this is a XOR B, and now A XOR B, again another half adder, that means another XOR, and the one input is the carry itself. That means, we can write this thing is nothing but my S is A XOR B XOR C, what just now I have drawn for the first circuit. Now, for the carry C, again this is my A B, and for the remaining portion, see this is A XOR B, this is A XOR B, and that is ANDed with C, and it is simple OR. So, just remember the previous one, that see this is C, this is actually the C, and this is A XOR B with A B. So, see this is C AND, here one AND gate is needed and one 2 input XOR gate is needed, and for this A B one, again this is a 2 input AND gate. So, what we have done, say this C, for this C, see that this equation is mainly doing that thing. So, this is my A B, actually this AND input is AB, this AND input is AB, and this AND in output, this is one input is A XOR B ANDed with C, and this is the AB. So, this C is C dot A XOR B plus AB. So, this is one realization. And this S is the A XOR B XOR C. Now, there can be many other realization possible for this full adder circuit. Now, again that what we have discussed for the half adder circuit, that is true, that what will be what type of gates are available for my realization. That can be the traditional AND OR gate realization, or that can be that multi input gates. Even it is a AND OR gate, that can be multi input gate, or it is a 2 or 3 input gates, or the XOR XNOR gates with the inverters also may or may not be there. With that realization it is possible. See, I can take another one. See, my S is A XOR B XOR C. So, my A XOR B XOR C, and my carry is AB plus BC plus C. So, simple that if it is a 2 input AND gate, only say I am thinking that my uncomplemented variables are not available. I want to realize a circuit where only the uncomplemented variables are available, complemented variables are not available. So, first I am realizing carry. So, AB, then BC and CA. So, these are the, then this is OR, this is my carry C. Now, say one XOR gate I have given. So, this carry is the one input, again A is another input, and C I can take B is another input. So, this is my S. So, this is also another kind of realization where the AND gates are needed, and see 2 input AND gate, this is 2 input AND gate, number of 2 inputs AND gate needed is 3, 3 input OR 1 and 3 input XOR, that is also 1, and always that the traditional things are there, that means one 3 input OR gate, 3 input OR gate, that we can realize by 2 input OR gate. Similarly, the 3 input XOR, that means I am writing OR or XOR, that can be realized 2 input OR or XOR. So, in real life actually there are several type of realization possible, and they consist of different type of gates. Now, another thing I want to mention, that what type of gates I want to select. Actually, that depends on the different type of parameters. That one is called that area, another is called that power. That means, now mainly our aim, that circuit we actually discussing, they are ultimately they are utilizing for preparing a chip or designing a chip. So, mainly the parameters that we have to consider, that one is the area, means always we try to reduce the number of gates, as well as another point we can tell, that always we try to realize minimum input gates or gated circuit. Means that if the 4 input XOR is needed, then always that we will use that 3 2 input XORs, and another is the power. So, for different type of or different gates consumes different power. So, if we see that my XOR is consuming more power than AND OR circuit, then depending on that what type of circuit or what type of application actually we are for what type of application the circuit we are designing, then we will select that type of gates. So, mainly these are the two criteria for selecting the gates for different type of circuit realization. So, if we want to summarize, mainly by using these two type of adders, what we have shown, that for each type of adder, half adder and full adder, a number of different type of realization is possible, and mainly depending on the application, that means whether we want to reduce the area or we want to reduce the power, that we will select that type of realization consisting of AND OR gates or XOR gates or the NOT gates, etc. Okay. Now, today's this quiz question is, again this is a combination circuit design and very similar type, that we have discussed the adder, and now the problem is design a combination circuit that performs a subtraction of 2 bits, mainly the addition we have discussed and the subtraction. For similar to the half adder and full adder, first we have to do the half subtractor and then it is a full subtractor. So, first we have to define what do we mean by half subtractor. Half subtractor means that again this will be a single bit minus, where that previous borrow bit the where for addition it was the carry bit and now it is a borrow bit, that is not considered, and for full subtractor the two operands as well as the borrow bit from the previous subtraction should be considered. So, these are the quiz question for this current lecture. Okay, thank you. In the last class, we have read how to design the different type of adders, mainly the half adders, the full adders, and the different type of realization using a variety of gates. Today we will see how we can design the subtractor circuits. Now, a half subtractor is a combination circuit that subtracts 2 bits and produces their difference. It has also an output to specify if a 1 has been borrowed. So, the similarity with the adder is that in case of addition, it was for addition it was the carry signal. For addition, one sum and one carry has been generated. For subtraction, that sum is replaced by the difference because it computes the difference, and the carry, here the carry concept is actually the borrow. So, we denote this as a B and the difference as D. Now, how the operator operates on the two operands. So, again first we see the addition operation. See here that 0 plus 0 equal to 0 and the carry is 0. 0 plus 1 is 1, carry is 0. 1 plus 0 is 1, carry 0. 1 plus 1 is actually 1 0. So, sum is 0 and carry is 1. Now, see, if I want to change this operation addition as subtraction, then what we can do, this 0 plus 0 equal to 0. So, as if one operand from here, say this 0, I can